So now we enter session 1 of the public lecture series, and I first welcome Mr. Keanu Nichols, who will present highlights on his research conducted while at the summer internship. Keanu is a third-year undergraduate at the University of the West Indies, studying computer science. He's a former Google Summer of Code student that worked under a Linux Foundation project called Chaos. He is also an undergraduate machine learning researcher with TT Labs, working under Professor Patrick Hossain. Keanu conducted research in deep learning on satellite imagery for tsunamis and cloud classification at NASA. Mr. Nichols will now present on his research.
Hi everyone. I'm assuming you can hear me. So I'm going to be talking about what I worked on for the summer. Okay. So my project was deep learning on satellite imagery for tsunamis and cloud classification. So you can see me there. And then those are my mentors, Brian Colton and Michael Furlong. So they both work at NASA as contractors. Right. So this is the introduction. So what is Delta? Delta is deep learning, training, and analysis. So this was a project I worked under along with Tevin, but we worked on like separate projects. So what is Delta? Well, Delta is meant for scientists, whereby they want to be able to allow them to use state-of-the-art machine learning models for different tasks. So for example, you can see a picture here. So this is a Landsat image, Landsat being one of the satellites they have up there in space. So what they wanted to be able to do is to be able to take that Landsat image of somewhere on Earth and be able to determine where the flooding actually took place. So this is a binary classification type of problem. So this could be used for floods to be able to determine where has been affected. So this was one of the things that Delta has done so far. So what I had to do was to be able to extend Delta to work on different problems. So my projects, I actually worked on 2 projects during the summer. So the first one is to determine which buildings were affected after tsunami. The second project was to segment clouds in a Landsat image. Right? So I'll be speaking about the first one, which is determining if buildings were affected by a tsunami. So this was based upon a data set that was done after a tsunami that took place in Japan. Right? So it's called the ABCD dataset, and we utilize to create a dataset. They used one of their own satellites from Japan, and so what they did was after the tsunami, they looked at the images from this satellite and determined based upon like people's responses and stuff. I think what they did was they allowed people to actually like classify from those images what kind of destruction happened. So this data set actually has only 2 labels. So the first label is if it was affected by the tsunami, and the second label is if it wasn't affected by the tsunami. And so they utilized the Ministry of Land, Infrastructure and Transport and Tourism to help classify using a survey. And so this data set was created using a paper that they published, and so we actually used that data set to incorporate it into Delta. So this is the actual process that I had to implement. So what we have there is we have a 6-band image. So when I say 6-band, there was the before image and the after image. So in an image, typically what you'd see online, it would be an RGB image, red, green, and blue. So the first 3 bands would represent the RGB, the before it was affected by the tsunami, and then you would have the last 3 bands, RGB, detailing the after image. So as you can see there, what I had to do first was, because they had the data sets in that kind of like gray representation, I had to actually separate the images for the before images and the after images. So that's how you have the before the tsunami, and then you would have after the tsunami. So I had to work on separating those images. And so after that, what we wanted, the goal of the project was to be able to create two different models, machine learning models. When I say machine learning, what you would normally do is you would give an input to a certain kind of complex mathematical function that will be able to learn certain features of that data and be able to better, if you were to give it new data, it would be able to classify it as, in my case, if it was affected by the tsunami or if it was not affected by the tsunami. So, so what we wanted to be able to do was to create two different models. The first model would be trained on the after images, and so if you give it a new image, it'd be able to determine if it was affected by the tsunami. And then we wanted to create another model that was trained with the before and after images side by side and determine what kind of accuracy that had as opposed to the model that was just trained with the after images. So in the paper that we were looking at, they actually trained it on a convolutional neural network. Now, to explain, a convolutional neural network is a very state-of-the-art machine learning algorithm that is used in today's world for a lot of computer vision related tasks, so a lot of things with respect to images. So that's why we train using a convolutional neural network. So as you can see here, this is the actual architecture of the CNN that we utilize. Yeah. So now we actually want to talk about the training time for trying to do this. So when we actually when we implemented the CNN, the convolutional neural network, in the paper, it detailed that it would take around 12,000 epochs. Now, to explain what an epoch is a run through the dataset. So for this dataset, it had around maybe 6,000 images, right? So we were going to be able to, put these, input these images into the convolutional neural network, and we were going to do it for 6,000 images. And what we realized when we were training it was that for one epoch on my laptop, which has an i7 processor, a CPU, it took 90 minutes, right? And in this paper, they proposed that it would take 12,000 epochs. So that was going to be 12,000 by 90, which most likely would have been longer than my internship. So the next thing that we tried to do was we tried to do it on a better computer. So my mentor had a i7 8th generation CPU, and so this cut down the time to 30 minutes, which still would have been taking too long. So the next step was to actually run it on the Pleiades supercomputer. So this is one of the supercomputers they have at NASA. When I was looking at it online, I think I saw that it was like number 16 in the world in terms of supercomputers. So it's pretty like state-of-the-art. So what I actually had to do was one of the persons we were working with had to actually, they would use a code that I had and submit it to the supercomputer, because this is being used by a lot of people at NASA. So you have to there's certain times you are only allowed maybe around 25 hours to run your code, and if it doesn't run in that time, well, you can no longer use it. So there's like a certain time limit. So when we actually ran it on the supercomputer, it actually took 8 minutes, which would still be too long. So the problem here, I guess I should explain. So what was happening was that when we were submitting the images to the CNN, the convolutional neural network, we realized that it wasn't learning anything. Whereby, so for each of the images, it kept giving the same kind of output. So whereby, if you were given the image, it would classify everything as either being, all of them would be affected by the tsunami, or everything was being not affected by the tsunami. So what was happening here was that it wasn't actually learning anything. So when we were inputting it, we realized that it wasn't, it was forgetting everything that it had learned before. So we tried to work on different ways of maybe determining if maybe we needed to shuffle the data sets or something. So we spent some time working on this. And then we came to the conclusion that maybe something may have actually been wrong with this data set. But there still needs to be some more like rigorous testing for it. But we still created kind of like a pipeline in which you could like submit images and be able to determine if it was affected by a tsunami or not. Because all of these images are in a normal format, so it could be utilized for something else. So that was my first project. The next project was actually the, this is the cloud segmentation. So this actually utilized Landsat. So this was a data set that was built using the Landsat 8 satellite. It composed of RGB images, so your typical images you would like see online, and then near infrared. And this data set actually used 700 epochs, which was actually very different from the other data set we had used, which was surprising. Well, it was a bit strange that that other data set used that many epochs when this one only used 700. And another strange thing about the data set we had used before was that they never actually gave the specifics of how we had to utilize. They didn't specify like the architecture, well, the exact architecture fit. So we actually had to do some different testing and see if different models might have learned something, but it didn't. But for this one, they were a bit more detailed, so we were actually able to see how they did their architecture and the specifics of it. So we use a fully convolutional neural network, and this is just the paper that we use. So what did we actually, the process? So for the process, we actually looked at that Landsat image. Now, one big thing about this is that the difference between the data set before and the data set after is that the data set before, the images were like 64 by 64 pixels. So it's kind of small, right? That's like on your computer, it's like a very small section. This image, however, was around 7,000. So it was very large. So we have the actual normal image, the Landsat image, and then we actually have the ground truth. Ground truth being each of the individual pixels will label as either being there's cloud covering it or there's no cloud covering it, right? And so what we did was that we actually fed the image and the label into the neural network, and we were going to create a classification model. So we actually were able to create this model. One of the issues, however, was that because of the method that we were using in Delta, because we want to be able to accommodate for persons who are going to be using, since these Landsat images are very large, right? Typically, if you try to submit like a small image, it's fine, your computer will be able to process it. But these large images, we actually looked at chunking it. So what chunking means is that we would take like different sections of that image. So we take one section here, one section here, one section here, and we would look at the actual center pixel of that image and use that as the label. So it involved like a good amount of maths to be able to utilize that, but we were able, so they already had that code written up because of the previous flooding problem, so I was able to utilize that code. And so we would chunk the images. So what I was actually feeding into the network was actually a smaller like subset of it. And one of the things we looked at doing was actually shuffling the data because one problem that could occur is that if you don't shuffle the data and you say, for example, you give it a bunch of data, like maybe 1,000 images, and they all have a single label, as in all of them have clouds in them, then the neural network might just learn about those features of that image. And if you try and give it more images that do not have a label of one, it might not pick up on that, and you wouldn't be able to learn anything. So we would encounter the same problem that we occurred in the first data. So we actually look at shuffling the image. And so when we shuffle the image and fed it into the neural network, and we tried to do it on a test image, we realized that it actually started to reconstruct the image that we were doing before. One problem, however, is that it was it wasn't a whole image, so it was kind of smaller. But this could be useful, however, because if you, say for example, one of my friends actually, who was another NASA intern, she was working on some stuff looking at like Chile. And she had to actually kind of like hand label some of the images. And this could be useful, whereby you would be able to determine from an image how much of it actually have clouds in them. So if you were to actually hand label it, say you have like, maybe you have to hand label like maybe 50 images, but a good amount of the images are actually covered by clouds, but you only realize this when you actually like look at the image. Because depending on the size of the image, sometimes you can't even see like a small thumbnail of it. So this model could actually be used to be able to disregard those images. So yeah, so there's just some future work to be done on this, but I was still able to do like a good amount with respect to it. And so the next part is just going to be some of the lessons that I learned while there with the internship. So I learned about using BI/BIM, which is a very it is very hard, because the first time that I used it, I didn't even know how to exit the editor. You actually have to type in a command. It's like :Q, which was a bit surprising. Because if you try and just like say you use the exit sign, the close symbol, because it's actually running, you could like delete data that you were working on. So you actually have to know the commands to like write it and quit. But it's very useful in terms of like you're able to write a lot faster than in typical text editors. So all my mentors were using this. They were using BI, and actually, I would say I was a bit forced to learn how to use it. But it was now I can't use normal text editors. I have to use BIM. So I had to work on looking at a lot of research papers, because I had to be able to understand like what was being used for state-of-the-art like stuff. So like learning about how convolutional neural networks are used a lot for image recognition and segmentation of images, and being able to determine like if a problem was solved, like maybe what we could add to it, or how could we incorporate it into something like Delta, so that we scientists could actually use these type of machine learning models for like different tasks that they have. This summer, I crashed my computer many times. I crashed my computer like maybe more than 10 times. So that was fun. I think my computer is very happy I'm no longer an intern there. The next step, I learned about using TensorFlow/Keras. So because we were working with a lot of large images, TensorFlow, which is a project made by Google, so whereby they're making it easier if people are working on very large data sets to be able to load data. So for example, the data that we were working with, we were using something called like lazy loading, and what that means is that because it's so the data is so large, we want to be able to not load all the data right now. So yeah, so I looked about using that, and I looked at being able to increase the speed of Delta using large images, and I found an issue where chunks were being disregarded in the data set. And so the future, what can be done in the future is to verify the results of the tsunami dataset, and to be able to extend Delta to other topics in the earth sciences, because I was only working on tsunamis and cloud segmentation, but it could be used for different things, for like disaster response and all of that. So yeah. And so I just want to acknowledge with my mentors, Brian and Michael, because I had a lot of questions throughout the internship, and they were gracious enough to answer all of them.